This is part 7, Transformers Architecture of the series AI for Everyone. Transformer Architecture, the power behind modern LLMs. Now let's talk about transformer-based architecture, which powers today's large language models or LLMs. On the screen, the diagram shows the transformer architecture. Some models, like T5, use an encoder-decoder setup, while BERT uses only the encoder. However, ChatGPT is a decoder-only model, meaning it generates text using only the decoder stack in an autoregressive manner. Before transformers, recurrent neural networks, RNNs, and their advanced variants like LSTMs and GRUs were the best methods for natural language processing, NLP tasks. RNNs and their variants were widely used in early voice assistants like Amazon Alexa, Google Assistant, and Apple Siri for tasks like speech recognition and natural language understanding. These models were capable of processing sequences and capturing context, but they had major limitations like sequential processing. RNNs process words one at a time, making training slow and computationally expensive. Limited context window. Due to the vanishing gradient problem, RNNs struggled with long-range dependencies, meaning they couldn't retain context over long sentences or paragraphs effectively. How transformers overcame these issues. The transformer model, introduced by Google in 2017 in their seminal paper titled "Attention is All You Need" by Vaswani et al., solved these problems by introducing parallel processing. Unlike RNNs, transformers process all words simultaneously instead of sequentially, making training significantly faster. Positional encoding. Since word order is important, but transformers process words in parallel, positional encoding ensures that the model retains word order information. Self-attention and multi-head attention. Instead of relying on sequential dependencies like RNNs, transformers use self-attention mechanisms to dynamically weigh the importance of words relative to each other. Larger context window. Transformers significantly improve the ability to retain and process long-range dependencies compared to RNNs. However, practical context windows in LLMs are still constrained by memory and computation. Due to parallel processing and architectural scalability, transformers enabled the development of extremely large models, with billions or even trillions of parameters. We will dive deeper into the inner workings of the transformer later in the video, exploring attention heads, feed-forward networks, and layer normalization, which collectively make these models so powerful. Here are some popular encoder-only, encoder-decoder, and decoder-only models. On the left in light blue are encoder-only models. In the middle in orange are models that use the encoder-decoder architecture. On the right in light purple are decoder-only models. Encoder-only. Large language models, LLMs, are particularly suitable for tasks that involve understanding language. It cannot generate new content. Here are some common use cases. 1. Classification, encoder only. LLMs can be used to classify text into different categories based on the context and semantics of the text. 2. Sentiment analysis. These models can evaluate the sentiment or emotion expressed in a piece of text. This is particularly useful in areas like customer feedback analysis, social media monitoring, and market research. 3. Miscellaneous text classification. Encoder-only LLMs can handle tasks that involve classifying text that may not have a clear or strong relationship with one another, making them suitable for real-world cases. A popular example of an encoder-only LLM is the bidirectional encoder representations from transformers, BERT model. It's widely used in various natural language processing, NLP tasks, due to its ability to understand the context behind words with similar meanings. Decoder-only large language models, LLMs, are primarily used for tasks that involve generating language. Here are some common use cases. 1. Content generation. Decoder-only LLMs are often used to generate content such as stories, blogs, or other forms of written content. 2. Text completion. These models can predict the next word or sequence of words in a sentence, making them useful for tasks like autocomplete or predictive typing. 3. Chatbots and conversational agents. Decoder-only LLMs can generate human-like text based on the given input, making them suitable for creating chatbots and conversational agents. 4. Summarization. These models can be used to generate summaries of longer texts. 5. Translation. While typically an encoder-decoder task, decoder-only models can also be used for translation by treating it as a text generation task. A popular example of a decoder-only LLM is the Generative Pre-trained Transformer 3, GPT-3. It's widely used in various natural language processing, NLP tasks, due to its ability to generate coherent and contextually relevant sentences. Encoder-decoder. Large language models, LLMs, are used for tasks that involve both understanding and generating language. Here are some common use cases. 1. Translation. Encoder-decoder LLMs are often used for translation tasks where the model needs to understand the text in one language and generate the equivalent text in another language. 2. Summarization. These models can be used to generate summaries of longer texts. 3. Question. Answering. Encoder-decoder LLMs can be used to answer direct questions based on the context provided. 4. Text-to-text transformation. These models are also used for tasks that involve transforming the input text into a different form of output text. This chart represents an evolutionary tree to depict the various model and what type of transformer architecture they are using, like encode-only, encoder-decoder, or decoder-only. They are mapped to the timeline on the y-axis. On the bottom left, you can see a branch in light brown color is showing very early models which were used to create embeddings. Then there is branch in light pink or red, as may perceive it, showing encoder-only models. The green branch in the middle is showing models related to encode-decoder architecture. On the right, the branch in light gray color is showing decoder-only models. Also, notice that model names with white background and border around them are closed source ones, like GPT-4 and BARD on the top, while the models with a light blue background and no border around them are open source one. Let's try to visualize the steps inside an attention head. Note that this is a highly simplified explanation to help understand the concept. The first step is to convert words into tokens, and then convert these tokens into numerical vectors. The next step is to apply positional encoding to the vectors. Assume that what you see on the screen has already completed these steps. Next step involves matrix multiplication, where each word becomes contextually aware of other words. This means that a word like apple understands its meaning based on the context provided by surrounding words and resolves itself to fruit or apple as a company. There are multiple attention layers and many multi-layer perceptron, MLP layers, through which these calculations continue. At each attention layer, words are enriched with semantic meaning by learning their relationships to other words in the sentence. At the final layer, the model predicts the next word, which is then appended to the previous sentence, and the updated sentence is fed back as input in a repetitive manner. This repetition is known as auto-regressiveness, meaning the model generates text on its own, one word at a time. Let's look into matrix multiplication in detail. You can see the words from the same sentence are represented both horizontally and vertically in the matrix. After multiplying the vectors for each word, the result resembles a score matrix, where each number represents how relevant a word is to another word in the sentence. This is also where the intelligence emerges, as the model learns relationships between words and kind of becomes aware of its surrounding context. However, there is a crucial step: masking future tokens. We do not want later words to influence earlier words, as this would reveal the next word before it is predicted. To achieve this, before applying the softmax function, we convert these unwanted values to negative infinity. After softmax is applied, these negative values become 0, effectively preventing information leakage from future words to the past words. This is how the matrix looks after applying masking and softmax. The size of the attention matrix is proportional to the square of the context size. To compute this efficiently, transformers use query Q, key K, and value V matrices cache. Scaling the context size is non-trivial, but many innovations have been developed to increase it, as shown on the screen. Modern large language models, LLMs, do not rely on a single attention head. They have multiple attention heads. For example, GPT-3 has 96 attention heads, each with its own query, key, and value matrices. So now you can see how transformers have effectively replaced and overcome the limitations of RNNs, mainly one, sequential processing of RNNs versus parallel processing of LLMs. 2. Very small context size due to vanishing and exploding gradient issue to substantially very large size of context window in LLMs. Also note how LLMs maintains the orders of words using positional encoding, which allows it to process all input words at once and that too in parallel. Similarly, the magical matrix multiplication in the attention head, where intelligence seems to emerge as words are becoming aware about their own meaning in relation to other words in the sentence, much like how humans process the information. Let us now explore GPT-2 Small, which is 124 million parameter model that can run in the browser to understand the inner working of transformer architecture. We will get into details of each component, but let's first explore the working of it. Notice the input to LLM on the top. The last word C is highlighted in pink color to indicate it is a generated output in response to the input sentence that we provided. You can see on the right side, LLM does not just generate one output, but many of them, and assign the probability of likelihood to each word. Now, if you click the Generate button again, the projected out word is appended to the previous sentence and is fed back as input to LLM. And this process of appending the output back into input continues, and this is what we call auto-regressive nature of GPT models. Also notice how LLM just generate one word at a time. It is a next word predictor machine. In our case, we had to click Generate button, but in real LLM, you don't have to do that. In our case, model is designed to take no more than 12 words and it stops. Also, you might have noticed the effect of input sentence getting longer on the size of K, QV matrix in the center, KVQ cache matrix getting bigger and bigger as the input sentence was growing longer. Technically, LLMs can handle very large contexts, provided the underlying hardware can support. We will take about memory size requirements later, but you see the reason why LLMs are usually created with limited context sizes. Also, the larger context window introduces another problem. There was a paper titled Lost in the Middle, published by MIT. The study reveals that these models often exhibit a U-shaped performance pattern. They process information most effectively when it's located at the beginning or end of the input context, but their performance declines when crucial information is situated in the middle. This suggests that LLMs may overlook or inadequately utilize details positioned centrally within lengthy contexts, as can be seen in the diagram here. So when you are consuming or using LLM, watch out for this behavior when your input to LLM is getting larger. Let us have another look at it. This time I want you to watch the effect of input put statement on K, QV matrices. Just observe how it grows large as we increase the word in the input. Now let's try again and have a look at how hyperparameters like temperature and top affect the generated output. Value greater than 0 for temperate allows LLM to randomly select the output word. As you can see, we have the temperature set to its lowest, and it is always selecting the first word. Let us now dive deep into the main components of Transformer Block. Here you can see the input words converted to tokens, and then positional encoding applied to the tokens. GPT too small uses 7, 6, 8 dimension for embedding. The next block is attention head, where dot product or matrix multiplication between query and key is carried out. This is where words become aware about their relation to other words. There is one query key cache per word. Since we have 6 input words, we have 6 query key caches per attention head. And since we have 12 heads, so we will end up with 6 times 12 equals 72 QKV caches. Let us drill a bit deeper into QKV cache or matrix multiplication or dot product. Here is the first matrix in the attention block. Remember from our previous discussion, we want to ignore the influence of current word on the past words. Here those will be on the right side of the diagonal. We will keep the values from the left side of the diagonal. Let's expand the attention head. The middle box is where the masking is applied, and softmax is where those values from right side of the diagonal are zeroed out. The cells or neurons that are grayed out are the ones that we don't need. The next layer is MLP. Here too, there are matrix multiplication. After attention is applied, the MLP block, also called Feed Forward Network, FFN, is used to attend the information non-linearly, allowing model to extract deeper features from the text. This step allows model to capture richer interactions that attention mechanism cannot do. Here, model learns complex hierarchical relationships. I hope this session has illuminated your understanding, making the complex AI landscape easier to navigate and comprehend. Hi, I'm Naunihal Singh Sidhu, a Microsoft Certified Azure Solutions Architect with over 25 years of experience in IT, specializing in AI-driven transformation, enterprise architecture, big data solutions, and digital innovation. Please feel free to connect with me on LinkedIn. Reference this channel when requesting connection.